All right, silly people, here's the situation. Did you know that um, if the de Broglie wavelength of a system of matter is greater than the box size that it's in, D, um, that you have to treat the system as being a quantum mechanical one rather than a classical one? Um, so let's look at various gases to see what that means for the temperature. So um, we have on the left-hand side, using the definition of the de Broglie wavelength of h over the square root of 3m kbt will be greater than d, the size of the box. Um, and we can solve for t, so I'm going to square both sides. We'll have 3m kb d squared, and then that'll be greater than t. And I'm actually going to rewrite it as t is less than 3m kb d squared. So the idea is if you have a, a gas or a solid um, with a temperature that is less than this value, then you have to treat the system with quantum mechanics. So quantum mechanics is a cold science. Um, and so I think it asks specifically for a gas of electrons in a box of side length zero point 0.3 nanometers. So, I mean, that's just a bunch of numbers that we're plugging in now. Bunch of boring numbers. We have Planck's constant, which is 6.62 times 10 to the minus 34 meters squared kilogram per second. We have the size of the box given us, which is a zero point 0.3 nanometers, which is zero point 0.3 times 10 to the minus 9 meters. We have the fact that it's a system of electrons. So the mass that we're going to plug in is going to be the mass of the electron, which is 9.1 times 10 to the minus 31 kilograms. And then we have finally the Boltzmann constant, Kb, which is 1.38 times 10 to the minus 23 kilogram per second squared Kelvin. Right. We can plug all those numbers in, and that's not actually h bar squared, that's just h squared, isn't it? Okay. Plugging those numbers in, we got that is t is less than 6.62 times 10 to the minus 34. That number is squared. Then we have 3. We have 9.1 times 10 to the minus 31. We got 1.38 times 10 to the minus 23. We got 0.3 times 10 to the minus 9 squared. Plug that into a calculator. I already did so. And I got that for electrons, that temperature is about 100,000 to 129,250 Kelvin. So pretty damn hot. So you can pretty much never treat electrons as anything other than a quantum system. So, interesting. We'll find that for a lattice of silicon molecules, where the mass of silicon is actually given by there's 28 protons or 28 bosons in a silicon nucleus. So you multiply that by the mass of a proton pretty much, which is like 1.67 times 10 to the minus 27. That is in kilograms. Um, but yeah, the rest of the numbers don't change. So for the silicon atom, or for the silicon lattice, kind of like a CPU, if you will, you'll have that it's less than 6.62 times 10 to the minus 34 squared over 3 times 28 times 1.67 times 10 to the minus 27 times 1.38 times 10 to the minus 23 times 0.3 times 10 to the minus 9. It's the same box. It's just full of silicon now instead of electrons. And so plug that into your calculator. I got that it was about less than 2.515 Kelvin. So silicon has to be really, really cold for you to treat it with quantum mechanics. So pretty much always you can treat a lattice of solid molecules as just being in the realm of classical mechanics, classical statistical mechanics. The next bit of the problem is asking us to look at the ideal gas equation. That is, that is PV equals NKBT. And just kind of use this equation in accord with what we've already used to think about what temperature things have to be given that it's an ideal gas. So we can think about V as being just D cubed, because if it's a three-dimensional box, the volume is just going to be given by D cubed. We're going to use that to solve for D squared to plug into this equation up here. So P D cubed equals N. We're just going to consider one particle, so N we're going to set to 1. We're going to have KBT, and then we're going to look at D cubed then will be KBT over P. And so D squared will be that stuff to the 2/3. And we'll plug that into our expression that we got before, that the temperature is going to be less than H squared over 3M KB, and then D squared was on the bottom, so we'll write it like P over KBT to the 2/3. And then just algebraically solve for T again. So we have T over here, and we also have T to the 2/3 on the bottom over here. So we'll multiply both sides by T to the 2/3. And then the rest will follow suit. We'll have 3M. You have KB to the 1 times KB to the 2/3. And then that's P to the 2/3 there. Simplifying a bit, you'll have T to the 5/3 will be less than H squared over 3M to the KB to the 5/3. P to the 2/3, and then raise everything to the power of 3/5. So you'll have T on the left-hand side. You'll have just 1 over KB there. You'll have H squared over 3M that we're going to be raising to the power of 3/5, and then 2/3 of the 3/5 is 2/5. So you have pressure to the 2/5. And so yeah, if a gas, let's say an ideal gas, has a temperature less than those quantities given there, then you have to treat it as a quantum mechanical gas. So Griffiths suggests that we look specifically at the case where you have a bunch of hydrogen atoms. Again, just looking at one hydrogen atom. In an atmosphere of pressure, so at sea level, and then with that, the mass of a hydrogen atom is about the mass of a proton, so it's 1.67 times 10 to the minus 27 kilograms, and just plug those numbers in. So T will be less than 1 over, if you're watching along at home, say it with me, 1.38 times 10 to the minus 23 for the Boltzmann constant, and then we'll have 6.62 times 10 to the minus 34 squared for the Planck's constant, and then 3 times 1.67 times 10 to the minus 27. Yeah, that's it. All raised to the 3/5 power, and then 1 to the 2/5 is 1. So plug that into your calculator, and you'll get that temperature will have to be about less than or actually about less than 0.067. Geez, 0.067 Kelvin, which is even colder than before. So, I mean, you pretty much can never treat hydrogen at sea level as a quantum system. You have to pretty much just treat it as a classical thing, unless if it's really, really, really cold. So, last thing is it does ask for you to check the numbers for hydrogen in space. So hydrogen in space, I mean, I'm going to be using the same equation that I did for the last part, is actually this one up top. Hydrogen in space is going to be less than h bar squared is 6.62 times 10 to the minus 34. We're squaring it. We'll have 3 times mass of hydrogen, again, is 1.67 times 10 to the minus 27 kilograms. We have Boltzmann constant, so 1.38 times 10 to the minus 23. And then you're in space, and the average spacing between particles is 1 centimeter, so 0.01 squared on the bottom there. Plug that into your calculator for the last time, and you'll find that hydrogen in space, if you want to treat it as a quantum system, has to be colder than 6.339 times 10 to the minus 14 Kelvin. So colder than you could ever get, pretty much. So yeah, weird problem.